네, 감사합니다. 첫 번째 키노트 스피커로 스피치로 시작을 해보겠네요. 첫 번째 키노트 스피커는 에이바랩스의 파운더이신 에민 군 씨의 강연입니다. The Next 10 Years of Crypto라는 주제로 강연을 해주시겠는데요. So please welcome Emin with a big round of applause.
Hello. Hi, can you hear me? Great. It's wonderful to be back in Korea. Thank you very much for having me here. I always enjoy talking to Korean audiences. This is one of the most crypto-savvy countries out there. So I want to talk to you about the next 10 years. And we can't really talk about the next 10 years without talking a little bit about the last 10 years, as well as maybe perhaps the last 40 years of distributed systems research. So I want to give you a quick snapshot of where we are and what is to come. So crypto is here to stay. There's a new asset class in town. This asset class can do things that others cannot. There are a lot of things on Earth that have scarcity. But beyond scarcity, crypto offers something that people actually want and demand and can greatly transform the world. And there is great momentum behind this push. We all saw what's happening now with Facebook and Libra. And we can argue whether or not Libra is a cryptocurrency. It has some features that it has borrowed from the stuff that we have built as a community. It has many issues with it. But deep down, it shows us something. That is, the blue chip companies are now beginning to see the value of this technology. The internet came by, client-server technologies came by, and now it's the era of Byzantine fault-tolerant peer-to-peer technologies. That's what this is really showing us. And there's great frenzy in this space. If you talk to anybody in any large company, they will tell you that they have at least a few proofs of concept in the blockchain space. If you talk to any of the CEOs or CIOs of large companies, they will tell you that they have lots and lots of new projects. Most of these projects are not going into production. So there is a big gap between people's dreams, what they see as the coming new technology, and what that technology is capable of. So that's interesting. It's an opportunity for us to step back, and think about where we are as a community and what we've actually been able to deliver. So there are many undifferentiated products. Satoshi was brilliant. He came up with a very exciting new platform. He showed the world what it could do. And everybody else has been copying his vision. And today I want to show you a slightly different vision, both in terms of how it works at the lowest level, as well as the interface it exposes to the rest of the world. And what I think we're going to see is that we're going to see a space that's maturing. Just like the internet in 1962 when it got started, looks nothing like the internet we use today. Just like Ethernet that connects all of these machines together in the back room, looks nothing like the original Ethernet. We're going to see crypto change shape. We're going to see the technologies change shape drastically. And we're in the midst of that, and I want to tell you a little bit about the wavefront of research, about the most exciting things happening in this space, at least from a technologist's perspective. And I will start out, and I'll try to structure this across three different axes. I believe that there are three huge impediments to the adoption of this technology. Those three impediments are scale and performance that comes along with it. Simply put, first-generation platforms cannot support the scale, the performance, the latency needs of the digital assets we want to place on blockchains. If you want to buy something with this technology, you simply cannot afford to wait 60 minutes. That's just crazy. When we come to usability, there's a great gap between what we can do, what we can do as technologists and what ordinary people can do. And even as technologists, actually, there's a big gap between the API that these systems offer and the APIs we would like to build on. I will expand upon this in a second, but the bottom line is, if you want to build a system, if you want to build a company based on a platform, I'm sure you've all seen talks by many different people pitching platforms to you. Not one of those people is in a position to provide a strong guarantee to you. Not a single one. They all build a network that's best effort. And if you were crazy enough to build a company on a crypto platform, you're essentially saying, I hope that things work out. It's like, this is like the gesture that you do in the US when you're sort of saying, YOLO, let's hope for the best, let's hope that luck is on our side. You cannot build a strong guarantee. There's no foundation to anything that you build on top. And finally, there is this governance issue. These platforms are decentralized by nature, and therefore it becomes very difficult to evolve them, to change them as the needs of your users change. And today I'll talk to you a little bit about sort of new things hot off the research press that address all three of these hurdles. So let's go back to the beginnings of distributed systems. The problem of consensus lies at the heart of every blockchain. The core issue here is we have a large number of machines across the globe, and we'd like all of them to expose the same information to everybody. It would be an enormous failing, for example, if Erica thought that I had X number of dollars, and June thought that I had some other number other than X number of dollars. They all have to agree. This is at the core of the consensus problem. This was recognized very, very early on, in the early 70s. It was formalized, and the frameworks were established for approaching this problem by two great people. One of them is Professor Barbara Liskov of MIT, who's currently retired, and the other one is Leslie Lamport. Both of these visionaries have Turing Awards. They're fantastic people who set up a very firm foundation for a large class of protocols. They set up what we call the classical protocol family. Okay? So all of these classical protocols are voting-based protocols. And there are many, many, many of them. And the academics, people in my community, essentially mastered these over the course of about 30, 35 years. And along came Satoshi Nakamoto, and he looked at this enormous family of protocols, and he said, all of these are unsuitable for what I have in mind. Why? Because all of them require that every participant know who else is in the system. And to do that, you need this knowledge of who the people are who are in your system, and that requires a permissioning step. There are other problems with the classical family. All these protocols require all-to-all communications, essentially, and that requires quadratic complexity, n-squared complexity. I have to talk to all of you, you have to talk to everybody else in the room, and that means that the room cannot be very big. And in fact, this is why you're seeing a lot of the protocols who are adopting classical protocols, a lot of the projects adopting classical protocols cannot scale beyond 100 validators. That's the design goal for Libra, for example. And just pretty much Ethereum 2.0 is aiming for 64 validators, EOS 21 validators. So we had that all the way back from the 70s, all the way, up until 2009. And Satoshi came along and he said, look, these protocols, they're great. They do what they do, but that's not what I want. They're not sufficient for building open, large-scale permissionless systems. And he invented his own consensus mechanism based on proof-of-work mining. You all know how that works, and you all know how the sort of story played out from then on. Bitcoin showed us what is possible. And yet Bitcoin suffers from a large number of limitations that I'm going to talk about. There was one interesting thing that happened in the recent past. About a year ago, there was a new protocol unveiled called Avalanche. And it completely changes the game. It's not like, essentially it combines the best of classical with the best of Nakamoto consensus. So, as I said, classical people have the two Turing Awards. Nakamoto has about $10 billion in the bank, or in the blockchain rather. And now we have Avalanche. And I want to talk to you a little bit about Avalanche because it really changes the game, and it really changes what we are capable of as a community. So let me go into this. If I look back at Nakamoto's style, so proof-of-work-based systems, what I see is a protocol family that has very long finality. So for Bitcoin, you need to wait 6 confirmations at least, and that takes about an hour for the case of that chain. And in the other case of Ethereum, it takes, again, substantial amount of time for people to be assured that the blockchain cannot revert. These systems have low throughput. So Bitcoin is about somewhere between 3 to 7 transactions per second. 3 to 7 transactions per second is a couple of supermarkets in Seoul on a weekend. Okay, so that is not the kind of system with which we can take over the world. That is not the kind of system with which we can replace the US dollar and the euro. It's just not going to happen at that rate. You need much more throughput. And it wasn't clear until recently that we could reach Visa speeds. Visa does somewhere between 2,000 to 5,000 transactions per second. Bitcoin core developers were going around the world saying, we will never be able to achieve this. It's too high, and therefore we must go to layer 2. And they are right. You cannot achieve this safely with proof-of-work-based technologies. And of course, underneath all this, so why are we doing all this proof of work? We're doing it for getting decentralization, this really crucial property that we want in these systems. But are we really getting it? That's a really interesting question. If you look carefully at the Bitcoin blockchain, there are only 19 mining pools. So it's not all that decentralized. And the hash power tends to consolidate in the hands of a few entities. There are only so many companies that manufacture the mining rigs. There are only so many people in the world who have access to cheap electricity. And therefore, and also the mining game is a winner-takes-all game. The person with the lowest operational expenses is the person who remains alive at the end of the day. So we see this constant move towards centralization in proof-of-work-based chains. And of course, overall, there's enormous energy consumption as well. If you sum total the amount of energy going into cryptocurrency mining, it's about 4 nuclear power plants worth of energy. That's substantial. We could put that energy to use in a myriad of ways, in a large number of ways in different industries. Now, what's happening? In the last year, we saw a lot of projects look at this and try to move to a different basis. And what other basis do they have besides proof-of-work mining, besides Nakamoto? Well, all they knew was to go back to classical protocols. So that's why you've been seeing a parade of people probably go through Seoul, just like I'm up here now, come to you and say, hey, we have a new protocol for you. And what they're really doing is they're going back to the 70s, back to the 80s, back to the 90s, and dusting up an old classical protocol. And we already had those. They're not a new invention. They just got dressed up for you. But regardless, it's an old thing. And they all have their own problems. They cannot scale themselves to large numbers of validators. They trade off decentralization. We saw with EOS that when you have only 21 validators, they tend to form voting cabals. I will vote for you, you will vote for me. We create a cabal and we keep each other inside the validator pool. So these are all incredibly problematic situations. And of course, the most important one is these protocols are not robust. They're fragile. They're prone to actually falling apart. We haven't had one do this yet, but I'm sure we will soon. And it's kind of interesting how this will play out. But if you talk to the designers behind these protocols, they will readily tell you that they expect some consensus failures because the protocols are fragile. There's a reason why Satoshi invented a new consensus family. And it's because the classical family was not robust enough. So where are we now? As I alluded to before, there's a new consensus family in town. It's fundamentally different than everything you've seen. It is not a dusted-up new version of something we knew from before. It's called Avalanche, and it works differently. There are no leaders in Avalanche. It's a leaderless Byzantine fault tolerance protocol. Everybody participates in the protocol. Large numbers of people can participate. By large numbers, I don't mean a few hundred. I mean thousands, tens of thousands, potentially millions. You all, and I too, could become essentially the Jihan Wu of the Avalanche world. Anybody could participate, and anybody can play a fundamental role. And it's quiescent. That is, the protocol doesn't consume energy when there is no work to do, and it consumes energy in proportion to the work being done. It doesn't require constant mining, and it certainly doesn't require 4 nuclear power plants worth of energy. So there's no leak of value outside of the system. And it's incredibly scalable. So let's see, if I were to go through its properties, I don't have the time to go through how it works. So I'm not going to do that today. But let me tell you some of the interesting features. It's robust like Nakamoto. So it allows any number of people to come in and out as the system changes. It allows me to operate without knowing everybody in the system. It allows me and you to have slightly differing views on who exactly is in the system. None of these are true for the classical family. So in the classical family, we must all share the same view about who's in the system, which is what makes them fragile. It has very low latencies. By that, I mean 1 to 2 seconds for the case of Avalanche. That means within a second, you know that your payment is final. It has very high throughput. So that by that, I mean thousands of transactions per second. I'll show you some numbers in a second. It's very lightweight. There's no energy consumption when there is nothing to do. And it can even withstand larger than 51% attacks. So that's an interesting feature that, that Avalanche has. And it scales like no other. It scales much better than Nakamoto, and it scales better than classical. So let's talk a little bit about this. In classical protocols, you achieve finality by ensuring that a large number of the people inside your validator set that everybody knows and shares has agreed to a transaction. If I know that 66% of you have committed a transaction, using a classical protocol, I can say, okay, well, this thing is almost essentially permanent. That's great, but I have to all make sure that we share the same view. That's a big problem for us. And to do this, it requires, typically classical protocols require all-to-all communication. One could use Nakamoto, but if you use Nakamoto, then you have this problem about electing a leader essentially by doing this proof of work mining, which requires a lot of energy, et cetera, and it's limited, et cetera. In Avalanche, the way the protocol works is by constant polling of the audience. So to give you an example of how this works, essentially is if you're in a very, very big room and you don't know who's in it. Okay, so imagine we're in a stadium in Seoul, not just a small room like this, but a stadium with 50,000 people. What Avalanche does is every node examines the audience, asks a small number of people, hey, what do you think we should do with this transaction, accept or reject? And depending on what it hears back, it puts its own weight and preference behind what it thinks the crowd is doing. Now, the funny thing is, it sounds like a simple thing, sounds like it might work or it might not work, it's not so clear. But the Avalanche paper shows that it does work, and more importantly, it works very, very efficiently. So every node asks, say, let's say, on the order of 5 other nodes, some number of times, and after about a very modest number of rounds, after about 17 rounds, in the case of 10,000 nodes, they can achieve finality. So I poll the audience, I do it for 17 times, and by the end of that, I will be assured that we all have picked either the accept or the reject for that transaction. So what does that mean? Well, in a group of 10,000, I only ended up sending about 85 messages. That's an amazing amount of improvement over 10,000 squared messages, which would have been untenable with a classical protocol. And I spent no energy on mining, so that's again an amazing improvement on Nakamoto. If I look at the latency of these systems, here I'm showing, here we go, so the slides are over there. I'm showing Bitcoin latencies are about an hour, 6 confirmations. Ethereum latencies for equivalent security are about 500 seconds. Algorand, which is a new system from a colleague of mine at MIT, they have a cute trick that they use at the consensus layer. It's a classical protocol. I picked it as an example of a recent system. They get latencies about 50 seconds. Avalanche gets latencies of about a second. The throughput of these systems is really interesting. Bitcoin, as I mentioned, is around 5 TPS. Ethereum is about 15 transactions per second. Algorand, on a good day, in these numbers that they report, they somehow do not include the overhead of checking crypto signatures. But in any case, even with that, they get about 300 transactions per second. And Avalanche, because it's a new family, because it uses an entirely different mechanism for achieving consensus, ends up getting 7,100 transactions per second. That's in excess of Visa speeds. And most interestingly, it does this without making a compromise from decentralization. Okay? As I mentioned, Bitcoin has about 19 mining pools. Ethereum has about 11 mining pools today. EOS has about 21. And we make fun of EOS for having too few. And if you look at Avalanche, what it can do is on the order of tens of thousands to millions of validators. The Byzantine tolerance threshold in Avalanche is configurable. So that's interesting because if the attacker size, if the expected attacker is only on the order of 10%, then the system acts even faster. And one of the other interesting features is all these other systems, they degrade really badly when the attacker exceeds the expected threshold. So for example, in Bitcoin, you have a 51% attacker, your system is toast, it's done. In classical systems, if the attacker is 34%, the system is done, it's broken. Okay, so it provides no guarantees, the attacker is guaranteed to succeed. In Avalanche, it's robust. You can configure it for, let's say, 25% or whatever, let's pick 33%. You can configure it for a 33% attacker. The system will then guarantee to you a safety threshold, a safety probability of a problem every, say, 20,000 years. And if the attacker turns out to be a little bigger, suppose he's 35% of your network, okay, then it doesn't just collapse. What it does, it says, okay, well, I guaranteed to you that the safety problem was likely every 20,000 years. And now that the attacker turned out to be bigger than I thought, well, it turns out problems can happen, and my guarantee is blown, but they're not necessarily blown. That is, the safety violation can still happen, but it's going to happen every 10,000 years as opposed to the 20,000 years that I planned for. So that graceful degradation is really nice to have. Okay, so I want to switch gears a little bit and talk about the second problem that plagues everybody that copied Satoshi. So currently, all platforms provide the same lowest common denominator service. We build a network, we start selling tokens, this is what everybody does, and then you've got all these nodes in the network, they're all volunteers, and you've got this weird best effort service. There's not much you can build upon it because you don't know who's in your network, and you don't control what's happening. And these systems are designed to be extra legal. They don't integrate into existing systems. They provide a poor foundation. And in fact, the core problem behind this is everybody did the same thing by copying Satoshi. And what is that thing? They have one coin, they have one scripting language, and they have one network. And if you come in and say, hey, I'd like the coin to change how it behaves, I would like the coin to have a different kind of functionality, well, then you have to go fight it out with everybody in the network. Right? And in the Bitcoin case, they will all say, no, you cannot make changes. Right? So it's very difficult to change these systems. In Ava, it's entirely different. We envision a world where there are many, many, many different kinds of coins corresponding to different assets, different kinds of scripting languages, and multiple different kinds of nodes. So what this means is that we envision a world where every single non-digital asset, so whether that's real estate, gold, stocks, and similar things, bonds, derivatives, etc., we envision them to be on blockchains, a blockchain that can support the performance and scalability needs of these systems. In addition, not only do we have many, many different coins, for each coin you can pick the functionality it supports. So if you want to introduce a new coin on Ava, you can say, hey, I'm issuing a new coin. I would like it to have the Bitcoin scripting language, as well as Monero's ring signatures, as well as Zcash's zero-knowledge proofs. You want to have this, it's no problem. Or you can say something like, this is real estate. It obeys different rules. Plus, it has these anonymity features. Whatever you want to do, mixing and matching, you can do. But the most interesting thing is you also get to pick the network, the platforms on which your coin is supported. So you can say, look, my coin is not going to be a best effort, lowest common denominator service. It's going to be supported on special nodes that are, say, that I picked. And how did you pick them? Well, you picked them by giving them a certificate. Well, how did they get the certificate? They came to get the certificate by having a conversation with you, potentially. So this allows for you to have some control over how your coin is supported inside the network. And in particular, suppose you were issuing real estate, you want all these nodes to provide archival services for you. You want them to store their data for a long, long time. And so this is not lowest common denominator services. You're not going to get this out of riffraff who sort of joins a regular network. You're going to get this by enrolling people into your system. So one of the interesting features then is these people know what they're supporting, and they can actually extract value commensurate with the service they're providing. So they can say, hey, I know this is a real estate transaction. It's not like other transactions. I would like to extract a few $1,000s for recording this because it's a different kind of transaction. It's not just a hash. And finally, I'd like to talk a little bit about governance. The way the AVA protocol works, the Avalanche protocol works, is it lends itself to natural governance. Every other system has to bake in certain parameters at its onset, at creation. In AVA, these are subject to change. Any user of the system can say something like, hey guys, our network doesn't have enough nodes, let's say, and we should increase the minting rate to attract more nodes. Or vice versa, let's boost the price by decreasing the minting rate. And other key parameters like minimum staking period, and so forth are subject to change by any user. So anybody can actually have control of the Fed. So many other things that are fixed for all coins for all time are actually subject to change in AVA based on the user's preferences. So on this note, I just want to say that the internet was introduced in 1962. It came out of discussions that started in the 1950s and sort of started to be in the 60s. And the internet as we have it today is drastically different than the internet that we started out with. Crypto is no different. It represents a shift from the current money paradigm that we have to a very different paradigm, where a lot of the things that are done by trusted entities are now either automated or done by entities that we understand a little bit better, that we have transparency into. As we go forward, 3 things will be critical to adoption of crypto. One is scale and performance. It just cannot be done with single-digit numbers or double-digit numbers, and it cannot be done with snake oil numbers, right? I'm sure you've seen numbers in the millions of transactions range. All of those numbers, as you well know, are from concocted lab experiments. What I showed to you today is from a geographically distributed, actually properly done benchmarks. So scale and performance is key, and those are unachievable with the old protocols that we had before. Usability and interoperability are just as important, and I gave you a glimpse of how we plan to actually found these things on a better foundation, how we plan to base these things on a better foundation. And finally, flexibility and governance are also key. There is no way that we can fix for all time the behavior of the coin and expect it to get it right for the next, let's say, year or so, let alone for the next set of decades to come. There has to be input into that process. That input must come from untrusted entities, all of us, and we need to be in control of our money supply. So crypto will change the world, and I hope to do this in conjunction with all of you. So I'd like to wrap up by saying that Ava Labs is very, very excited to be building this new platform. We just opened an office in Korea, and we would love to have any interested developers come and talk to us. Thank you very much.